Today we want to test if two means come from the same population. Now, remembering, we first began our hypothesis test analysis for the mean with the standardizing formula. This formula grew from the sampling distribution. We looked at the sampling distribution of sample means, x bars. And the central limit theorem proved that this distribution was normally distributed. This gave us the standardizing formula. From this, we simply solved for the parameter we wanted to test, the mean, mu. We need to start again, back at the sampling distribution, but this time we have two population groups. So I have over here a bunch of x's. Here's my population number 1, and it looks something like this, who knows? And I've got over here a bunch more x's. So this is x2, and this is x1. And who knows, it looks something like that. And again, we don't know what the distribution looks like. We don't know its mean. We know it's got one. This one here has one too. Now what we're going to do is are these populations the same? Is mu1 equal to mu2? That's our test hypothesis. So I can write that over here. Okay? But I'm going to write it in a particular way. Okay? The sampling distribution will become not the distribution of sample means, but the distribution of differences in sample means. So what I'm going to do is this. I'm going to go in and I'm going to take a sample from group 1 and I'm going to get a sample mean. Let's say x bar 1. And then I'm going to go into group 2 and I'm going to get a sample mean, x bar 2. And down here, what I'm going to have is x bar 1 minus x bar 2. I'm going to subtract this one from this one. And that, big surprise by this time, is going to be normally distributed. So the distribution of differences in x bars is normal, which means that I can now, under here, translate it down to the normal distribution, just as I did before. I'm doing exactly the same thing. Okay? Now what we have then is the null hypothesis that mu1 minus mu2 equals delta naught. Now delta naught is a mathematical way of saying difference. So we use delta naught. So it's a hypothesized value versus mu1 minus mu2 is not equal to delta naught. By the way, it can be a one-tailed test if you want to. Okay? So we're looking at the differences in the two means. If delta naught is equal to 0, then we're asking the very straightforward question, is mu1 equal to mu2 versus the alternative, mu1 not equal to mu2. So what we have here then is this notion. Now the interesting thing is that this general form of the hypothesis allows us to test more complicated types of questions. Is this one bigger than that one by some number that matters to us? Now that number that matters to us might be driven by, let's say, differentials in prices or differentials in quality of the two distributions that we're looking at. So this is how we've done this with two different distributions here. Okay? We have two groups. Let's say the heights of men in 2000 BC and the heights of men in current time. We do not know the shapes of these distributions, so we draw them all squiggly like we've done here. Okay? And then we do this calculation, which gets us down to this distribution here. Okay? We do this many times to get the sampling distribution, as we've always done when we've done sampling distributions. And of course, big surprise, it's normally distributed. Okay? Regardless of the underlying distributions that we had before. Okay? This is our null and alternative hypothesis. Okay? Now all we really need is a test statistic. We need our formula. So the formula is going to look like this. And I'm going to actually need to sneak some space over here. It is a t distribution. So our calculated value of the t distribution is equal to x bar 1 minus x bar 2 minus delta naught divided by the standard deviation of the sampling distribution, which in this case here is s squared 1 over n1 plus s squared 2 over n2. S squared 1 is the standard deviation of the sample that we took from this group. S squared 2 is the standard deviation of the sample we took from this group. Standard deviation squared, and the 2n. By the way, the size of the samples that we take from each group does not have to be the same. Notice that this formula for the test statistic follows the format of all formulas of a test statistic we have done before. We are asking again the same question. How many standard deviations is the sample value, in this case this difference, from the hypothesized value, delta naught? The test statistic is the student's t-distribution because we do not know the population standard deviations. We have substituted in the sample standard deviations, our actual variances in this case. Unfortunately, the calculation of the number of degrees of freedom is a tedious formula rather than our simple sample size minus 1 we used before. For large samples, this formula will, in many cases, result in degrees of freedom that allow us to use the normal distribution table. Sadly, we will not know this until we work through the formula. So what about Goliath? Because sampling techniques on average heights of men 2,000 plus years ago are unknown to us, and we do not know the sample size and the standard deviations, let's content ourselves with another question. Are 19-year-old men significantly different in height than 19-year-old women in current times? According to the Center for Disease Control, the average height of a 19-year-old man in the United States today is 69.6 inches, or about 5'9". The average height of 19-year-old women is 64.2 inches, or about 5'4". The CDC also provides us with the standard deviation and the sample size for each group. The sample size for the men was 270, and for women, 225. The standard deviations were 1.3 inches for men and 1.2 inches for women. We draw the graphs and mark the critical value. So what we have here is as follows. Okay? On this axis here, we're going to have x bar 1 minus x bar 2. Okay? This, of course, is our sampling distribution. And as we learned earlier, this is normally distributed. Okay? So that's what we have. Now the hypothesized value is what we put here. And so off to the side, I've got the null hypothesis is that mu1 is equal to mu2 or mu1 not equal to mu2. Now remember, if delta naught is equal to 0, the general statement of this hypothesis is mu1 minus mu2 equal delta naught versus mu1 minus mu2 not equal to delta naught. Okay? So this is our hypothesis, and this is what we have here. Okay? Now what we do is we translate that information down to the z distribution because we're told by the central limit theorem that this is normally distributed. So here we have look like this. And what we do is if we want to be, let's say, 95% confident, okay, then what we will put in here is 1.96 and minus 1.96 here. Those are our critical values, Notice that I am using z here. Even though the test statistic is written as a t, the sample size is such that it's actually going to be in the normal distribution. So what we look at is this. I'm going to write it out as a t statistic, even though I'm using a z here. And this is going to be the x bar 1 minus x bar 2 minus delta naught divided by the standard deviation of the sampling distribution, this guy up here, which is variance of the first group, which is standard deviation squared, n1, plus the variance of the second group, that's a 2 there, divided by n2. Now, if we go about the process of calculating this thing, we're actually kind of stunning. It's 48.6 standard deviations. Okay? That number of standard deviations, of course, puts the calculated value dramatically into the tail. We must most certainly, we cannot accept the null hypothesis that there is no difference between the two groups in terms of height. On other matters, the differences are myriad and a continuing wonder.